My dear friends, welcome to Rajashekhar classes on applied data science with Python. This is lecture number 564. In this lecture, we will try to understand batch normalization. So, batch normalization is an other very interesting idea in deep learning. I think it is discovered around 2015, if I am not wrong, probably late 2014 or early 2015. So it is very interesting idea. So let me explain you the problem that we have with the deep networks. What problem does batch normalization solve? Remember, I have a network like this. Let's assume this is L1 means layer 1. It is fully connected multi-layer perceptron. L2 means this is layer 2. Let's assume this is my output. My output is Y cap. I have bunch of neurons here. Instead of drawing the big diagram, I'm drawing I'm drawing a shorter diagram, isn't it? If you go through my previous lectures, we used to draw big diagrams. Instead of drawing that big diagrams, just I'm drawing this simple diagram. Let's assume this is fully connected multi-layer perceptron. Now the first thing that we will do that we always do for any optimization problem is, given a data set capital D equal to xi comma yi, as a pre-processing step we perform data normalization on xi's. Data normalization, what I mean is mean centric and variance scaling, isn't it? It takes each of my xi's and I modify my xi's into xi tildes. What is my xi tilde? Xi minus mu by sigma. What is my mu? Mu is mean of xi, sigma is standard deviation of xi. This is your, what is this? This is basically data normalization. This is something that we learned long ago. We also understood why data normalization is required, isn't it? So that weights are interpretable, so that weights are make sense. Or let's assume there are just let me assume this is layer 1. There are 4 neurons in L1, that is layer 1. These circles indicate neurons, and 2 neurons in L2, layer 2. All these circles are neurons. Whatever they get input, that input is normalized. Imagine we have a network which is very deep. This is my input. Let me say this is my input x. X is input here. Let me say this is my layer 1. Let me assume this is layer 1. This is layer 2, then layer 3, then layer 4, then layer 5, then output layer, which generates what it generates Y cap. Let's assume I have deep network like this, isn't it? Let's assume this is also a multi-layer perceptron which is fully connected. Yes, lots of layers, not like this is deep neural network, as I can say. It is not deep. This one is not deep neural network, not deep. But let me assume this is deep neural network. Let me assume I have got so many layers. Let me say I have got so many layers here. For simplicity, let it be L1, L2, L3, L4, L5. What happens here is, if this input x, if this particular input x, what happens here? If this particular input x, remember input is if this input changes slightly, if this input x changes slightly, remember input is mini batch. What is this? If this input changes slightly, Remember, this input is mini batch because we are employing mini batch SGD techniques. We do not send the whole data as an input. We may send one point or small set of points. Let's assume we are operating the mini batch world. Let's assume this is my total data set and I am breaking this data set into batches, batch 1 to batch 7. In the first iteration, I will send batch 1. In second iteration, I will send batch 2. In third iteration, I will send batch 3, so on. In iteration 7, I will send batch 7. That finishes whole epoch, isn't it? Again, I repeat iteration 1, iteration 2, so on and so forth, isn't it? If my input even changes slightly, if my input even changes slightly, because I have a lot of layers, just see here L1, L2, L3, so on. In each of layers, it is doing some multiplication, addition, and transformations. Small change in input can lead to large change in the latter layers, especially if you have deep neural network. A small change in input can lead to a large change. The reason being, the small is multiplied by lots of weights, then lots of operations that are happening on small input. Let me show this with simple example, how small change can impact large changes. Let's assume I have two variables. Let me say whose first variable value is 1 and another variable value is 1.01. In next step, I will multiply with itself. Let me say 1 square means 1.01 whole square means I am getting 1.0201 whole square. Again, I am multiplying. I am squaring with itself. 1.0201 whole square means I am getting 1.040. If I keep doing this bunch of times, this will remains as 1. First one is remains as 1, but this value increasing dramatically. For example, if I keep doing this, let me assume I'm keep doing this 5 times, 1 is same as 1. What's happening here? If let me assume after 5 times, if you observe carefully, this 1 is remains same as 1, but this 1.0 is becoming 1.375. 1.01 is changing. This is 37% more than this. 1.375 is 37% more than 1. By just applying very simple operation few times, the operation here is I multiplied with itself. What is my operation here? I multiplied with itself. Here the operations are far more complex. If you take deep neural network like this, here operations, what it says here, your operations are more complex. In this particular network, deep neural networks operations are far more complex. If you are using sigmoidal unit, even ReLU, you are multiplying with lots of weights and you are summing them up, passing through ReLU unit or sigmoid unit. Again, you are taking output of L1. You are taking what's happening here? You are taking output of L1, and this output of L1 you will pass. Where will it pass? You will pass to L2. Isn't it? Out and passing through the next layer, that is L2. So small change here, the change is very small. What is the difference between 1 and 1.01? The change is only 1%. Here the difference is, if you observe, there is only 1% difference, isn't it? 1% change is only 1, because the difference between 1 and 1.01 is only 1%, but you repeated this operation 5 times, the change is 37%. Just see here, you are getting 1.375, 37. So what happening is, a small change in the input can lead to a large change deep in the network, isn't it? Let's take a neuron. Let me assume, let's take a neuron in L1. The input that it gets in each the input it gets in each batch. So I get a batch input, isn't it? What will I get to neuron in L1? Batch input to this neuron, which is in layer 1, isn't it? Basically, a batch is set of exercise. What is my batch? It is set of exercise, which is what I called my mini batch. What is that batch? Is known as mini batch. There is very little change in the input. If I change, there is a little change in the input, because at the beginning itself we have done mean centric and variance scaling, isn't it? So between each batch, because you have done the centering and scaling, you have done data normalization here. Between each batch, a neuron which is there in L1, yes, a neuron which is there in L1 does not see huge difference, isn't it? There is a small difference between batch to between one batch to other batch, isn't it? But taking a neuron which is at L5, because there are lots of operations, there are lots of operations that are happening between, let's say, batch 1 and batch 2. It sees a huge difference in the distribution of points that it sees. What does neuron at L5 see? It sees output from L4, and because I have so many operations, even though there is small change between two batches at L1, because it is passing through many layers, a neuron which is at L5, that is layer 5, will see batches being very, very dissimilar, isn't it? Just see this one, which means that the data is not normalized, because look at it. Sorry, look at it. Each of the neurons here, each of the neurons can be thought of a model. For every model, ideally you want your data to be normalized. The problem is, because you have these many layers, L1, L2, so on, even though at input level everything is well normalized, because of these many layers, neuron which is at very deep layer starts to notice that between one batch and other batch the distribution is very, very different. Ideally, what we want all the inputs are mean center. We want to have mean of 0, and variance of 1, isn't it? This is what mean centric and variance scaling means. This is what data normalization means, isn't it? This is what mean centric and variance scaling means. This is what data normalization means. This is the distribution of inputs that I want to see. But what happens is, for layer L5 in batch 1 the distribution is like this. Just see, in layer, I will repeat, for this layer L5 in batch 1 the distribution is like this. For batch 1 for batch 2 the distribution is like this. For batch 3 the distribution is like this. Just see, for layer 5 what's happening here. Your distribution, this is distribution for batch 1, isn't it? This is the distribution for batch 1, and this will be the distribution for batch 2. This will be the distribution for batch 3. That's what these batches means. If different batches are with different types of distribution, as distribution change, and they may not even normal, they may not even the Gaussian, as distribution changes, the neuron which is in the layer 5 can go crazy. Then the neuron, as distribution changes, for each batch the distribution is changing, therefore the neuron in layer 5 can go crazy, because every time it is seeing different input or different distribution of input. This problem is called internal covariance shift or internal covariate shift. Just see this particular diagram, different layers is seeing, just see different layers is seeing different distributions. Just see, this is one layer, this is another layer, this is another layer, this is another layer. Just go through this lecture. I will continue my discussion on batch normalization in my next lecture also, that is lecture number 565. Thank you very much.